Welcome to the exciting series of Mathematics in Robotics. Main goal of this series is to explore and analyze basic implementation and complex algorithms that utilize mathematical concepts, and the equations are being implemented inside of the code without we even realizing. In this first lecture, we are going to have two examples. The first one is robot motion in a circle, and the second one is robot motion to a specific point in 2D space. Both of these examples include mobile robot and a two-dimensional space. We have a code here that is a Python node in ROS2 package that is importing the libraries required, and driver node is the class, main function is called, and it publishes on turtle1 command velocity, which means it is going to be publishing a message that drives the robot. The next thing is it is calling this function, timer callback function, which is the function that is going to publish the data every 1 second. Okay, this message variable contains the values that we will fill and send to the robot that will make the robot take action about it. So I'm going to first bring in the turtle simulation. After that, I am going to run this node that is inside of my package. I will provide you the code as well. If I press enter, it starts publishing the data. ROS2 topic echo turtle1 topic list. This is the topic ROS2 topic echo turtle1 command velocity, and it is publishing 00 for all the values, as we have currently filled the values with linear x and linear y and linear z. I hope you understand what these things are actually doing. If I just change the value to 1 and if I now run this, it is going to start making the robot move in linear x velocity. I'm going to stop it. The concept that we need to understand is about this angular velocity. If I give the value of 0.5, build the node and run it, it is going to start rotating in an angular motion, only the rotation part. This is going to be not useful for our understanding, because this angular rotation or angular velocity in terms of controlling the robot is of no use, because it is just rotating the robot. In our scenario, we would be needing some linear velocity as well for the task that we want to achieve, that is to make the robot rotate in a circle. But the point is, what is the relation between this linear and angular velocity? That's the main thing that we need to understand. So let's first understand mathematically how things are working and how we can utilize the maths. Angular velocity is very important in mobile robotics because it is derived from a circle, and circle represents very important parts of a robot, mainly the wheels. So you need to be good at the formulas provided by the generic equation of a circle. The first one is circumference of circle, that is given as 2 pi r, and the reason is the distance from the origin to the end point of a circle is known as radius, the half distance. The complete is known as diameter, but we are not talking about that. So circumference is actually given as pi d and 2 pi r, which is equal to the total distance that we have around the circle. But we are looking for the velocity thing, and angular velocity is given as velocity, the linear one, over the radius. Now whenever we apply this derived formula with a constant radius, we always get a constant angular velocity around a circle. We can also provide linear velocity of different value, then angular velocity is going to change. One thing that you have to keep in mind is that angular velocity has a direct relation with the velocity, linear one, and it has an inverse relation with radius. So you understand what these relations actually mean. The point is, whenever we have this relation applied, what it is actually doing, if our robot is at this point, it keeps on moving along the boundary of a circle that is actually the distance in radians, and this velocity is being directly applied through a linear signal, and this relation then makes the robot move in an angular motion. Specifically in our scenario, we are going to be giving the linear velocity to our linear x, and angular z is going to be equal to linear velocity divided by radius. That is what makes our robot move in a proper circle, and this radius value is what we are going to give and control the circle that the robot produces. According to the equation that we studied, is this angular velocity is linear velocity over radius. I'll introduce two parameters, linear vel and radius. These are going to be taking inputs directly from the execution of the node, so I'll add these system argument that takes inputs while running the nodes. It's utilizing the sys library. Linear velocity is then going to be given to the message linear x, and for the angular velocity it is going to be linear velocity and the radius. Now you have to put your understanding into practice by this equation that we have, linear velocity divided by radius, and the relation is what you need to look at. Now let's build this code and run it. I have to provide these two inputs as well, so I will just get rid of the colcon build now, and I am going to provide 1.2 as linear velocity, and for radius I'm going to say 0.5. Going to press enter. It is going to start making the robot move. One thing you have to notice about this equation is the relation. That's what mathematics teaches us. Radius is inversely proportional to angular velocity. So if I increase the radius, angular velocity is going to decrease. For example, if I make it 1.5 from 0.5, this angular velocity is going to reduce, although the radius is going to increase. And regarding the linear velocity, I am going to increase it to 2.2. It is going to increase the angular velocity. Obviously it seems very simple, but you have to look at this angular velocity execution of this 2D simulation in terms of this formula to build intuition how it is reacting, and this is going to help us a lot in the next example we are going to be solving. Whenever it comes to motion of a mobile robot and you are writing an algorithm, you have to consider the mobile robot as a 2D point on a 2D plane. Conditions applied that your robot is moving on a plane surface. So when you are looking your robot as a 2D point, you write the algorithm, you perform all of the mathematical operations on it, then you come back to the robotic domain. In that you just need to translate the positions of the point into velocities of a mobile robot, and that's the conversion you need to do. And you should always keep the relation of the motion and velocities and acceleration to the xy coordinates of the grid on which the robot is moving. One thing that we have to look into in circle equations is trigonometry. Whenever we have a circle, in circle we have a radius, but we are not going to draw a radius here. We are going to say that according to trigonometry, if we move the point from this point to this point at this specific point, we have this sort of a right angle triangle, and along this axis we have y, positive y, and positive x. Along this axis positive x and the other one positive y. So this line here is actually the radius, and this one we can say it to be x. So by the equation of trigonometry and circle with the right angle, we can say cos theta is equal to x over r and sine theta is equal to y over r. And that becomes x is equal to r cos theta, y is equal to r sine theta. Remember that angular velocity is rate of change of the angle theta, which is this specific angle. So if we take these two equations and differentiate them, these equations become dx by dt, dy by dt, r cos theta into d theta by dt. Now here you have to keep in mind one important thing. These two things were positions and these two things are velocities. Both represent x and y points, and the velocities represent x and y velocities. Both velocities are dependent upon, you can see, this rate of change of theta, which is actually angular velocity. So angular velocity is directly linked with velocities in x and y, and so we can actually devise the velocities from the points on the circle. And so the velocity of a point on a circle can be described in terms of x and y components and the angular velocity. Similarly, you can go other way around as well by doing the integration. Some of the possible applications from this concept are that you can make your robot move in different shapes, and different patterns. And I think the possibilities are endless. All that is, they are limited by our own imagination. So let's move to the next example of making your robot move to a specific point. That's more of a trigonometric problem, and it is going to take some time to build the understanding, but I will make it easy for you. So here we have the go to goal node, in which we have libraries included. We are getting the command velocity. We are publishing command velocity to drive the robot as previous node. Here we are also getting the pose of our turtle. This is to get where the robot is in this simulation. We are creating a timer that is publishing 0.1 second each message, and in callback we update the data of our turtle bot, so we know where the turtle bot is, because we have to perform these calculations based on the position of turtle bot. And there are some variables and it is running. We'll go into deep detail what these equations are and how I got these formulas. So if I run the node, I have to provide 3 arguments. The first one is the location in X. I would say in X go to 2 and in Y go to 7, and in angular rotation I want you to go to 1.57 as it is in radians. I give these arguments into this code. It is rotating towards the goal. First it rotates and then it starts to move towards the goal, and once it reaches a certain threshold, it says that goal is reached and it gets out of the code. I can run it again and provide multiple arguments. Go to 9 of X and 1 of Y, and let's see where does it goes. It sort of first aim and then start to move. There is also some tolerance defined that makes this robot exit the code when it reaches certain threshold or tolerance. So let's see what these equations are doing and what are these conditions. For go to goal behavior, we need to find 2 main things: distance to goal and angle to goal. This means that let's say we have this axis. This one is positive x-axis, this is minus x-axis, positive y, negative y. We are considering only the first quadrant. In this specific quadrant, if we say that our robot is at this specific point, which we can say is 2 in X and 2 in Y, and we say that our goal location is this specific point, that is, let's say, 5 of X and 9 of Y. So what we are interested in is this specific distance, which is known as distance to goal. And when we talk about the angle, we consider the angle from this perspective, that this is the angle that our robot makes for the goal. So for now, we are not going to be looking into the angle. It makes things complicated. So let's say this is our situation in which we want to find the distance to goal. As we all know, distance to goal is actually to find the shortest distance without considering any obstacle in between, is the Euclidean distance. So Euclidean distance is x2 minus x1 squared plus y2 minus y1 squared. This gives us the shortest distance. For example, if I just calculate here the values, x2 is the goal, x1 is the robot, similarly y2 goal, y1 robot. Let's put the values. They are going to be equal to 5 minus 2 squared plus 9 minus 2 squared and whole square root. Solution is going to be 3 squared plus 7 squared, which is Euclidean distance 7.6. This is the Euclidean distance. Let's say we are now calculating another Euclidean distance. This was Euclidean distance 1, and for Euclidean distance number 2, we say that our point is somewhat near the robot. Let's say at this point, which is 3 of x and 3 of y. So we are directly going to apply the formula 3 minus 2 squared plus, for the y it is the same, 3 minus 2 squared, and it is going to solve for under root 2, which is 1.41. and you can see that the distance between this point, which is goal number 2, that is really close to the robot as compared to this goal 1. So the value of the Euclidean distance 1 is greater than value of Euclidean distance 2 because it is far. This is just common calculation. So now let's implement this into our code and see what our robot is telling us. We will start the code from this specific point where we have the main function, which is calling this class turtle gtg go to goal. It contains one publisher, one subscriber, and getting the data of our robot, and this function is going to be filled by us after the theory understanding. So we are now going to implement two things. The first one is Euclidean distance and the second one is angle to goal. These are the two things that we just discussed, so we have to implement. I'm going to rename it to be distance to goal and angle to goal. As far as the input is concerned, this goal X and goal Y are from this specific message, which is of turtlesim message pose message, which contains 5 fields. You can see X, Y and theta. There are linear and angular velocity, but we are not using them. For now, just stick with these as X2. Goal is our X2 and robot's current position, which is getting from this callback function, it is x1. So the formula was square root of x2 minus x1 squared plus y2 minus y1 squared. In our scenario, x2 is goal x and it is subtracted from self pose.x, which is robot pose. For y, it is goal y minus self.pose, and that's the robot pose in y. X2 minus x1 squared, y2 minus 1, that's the Euclidean distance. Coming to the angle to goal, it was by utilizing the inverse tangent function, and in our scenario it was y1 minus y2 over x1 minus x2. Goal y is our y2 and that is being subtracted by robot's y, which is x1, again goal x minus self.pose y. Tangent inverse of goal y minus the robot and goal x minus the robot's x. Distance and angle are done. We have to now look at the values and understand if they are making sense or not. For that, we are going to just say log message, as it is going to be logging. That message contains two things: a distance to goal, that is going to contain a float value, let's give it 3, and another thing is going to be angle to goal. It is also going to be containing a float value 3 digit. These values are going to be given from this format, and the values are distance first, the second one is angle to goal. These are going to be logged and we have to use the ROS logger. It is going to print out this message with timestamp. That helps a lot when debugging. It is going to compute both of these and let's see how does it looks like. Performing calc and build. Let's stop this and bring it again. ROS2 run robomath, and I want to move it to 9,9 and 1.57 is the rotation. I have to give the name of the node. So it is now logging the data. Distance to goal is 4.8, angle to goal is this. I have to artificially move the robot. For that, let's run another node, teleop key node, that is going to drive the robot. I can rotate the robot and there is no difference in the distance to goal right now. The values that I gave as an input are 99, so they are going to be something here. If I move the robot, now you can see the distance is decreasing and somewhat angle is increasing. That's why our logic is going to first fix the angle, reduce the angle to a point that it is set, and then we will make the robot start taking action. So you can see robot is above the point and that's why the distance has started to increase. Let me move exactly to 99 by looking at the distance, and the distance again starts to increase. So this is a task that is very important, and that is one problem of this task, is that if you move further away from the goal point, the distance starts to increase again, and although before that it was decreasing. So now let's look into the theory, how to control the robot in this situation. Let's solve our turtlesim step by step so we understand how it's done in the code. Current location of our turtlesim is 5.4 in X and 5.4 in Y, and you have to think it like this. This is the positive X-axis and this is the positive y-axis. Origin is at this specific point, but our turtle is at this specific point. So if we take this as a starting point, robot pose, and we say that we want to go here, which is somewhere 6.4 in x and in 9.2 in y-axis. This is our goal location. Let me calculate all of the values. Our Euclidean distance is 3.9 and our angle to goal is 1.28 in radians. So in radians, when we talk about a positive number, that means you need to perform counterclockwise rotation. So it needs to rotate. This is the 0, this is 1.57, so it has to move somewhere like this, which is again pointing towards the goal. Now let's do another example in which our goal is at this specific point. This is G2, and in X it is 8.1 and in Y it is, let's say, something like 3.2, given an arbitrary value. So for the calculation part, we are going to be getting Euclidean distance is equal to 3.48 and angle to goal is going to be minus 0.88 radians. So you can see for this specific goal we need to make this turtle turn in clockwise direction, and that is why it has a negative sign on it. I hope you understood the concept. You have to keep in mind one thing, that theory was really in a controlled environment, and in simulation, although simulation is still controlled environment than the practical real one, but in simulation there are a lot of chances of overshooting of the robot because it is running very fast in real time. And in theory I was doing it step by step and there was no problem for the robot, no problem with any motion. But in the simulation, robot motion is not in my control, but I will be controlling the robot behavior after the robot has given me the feedback. So a lot of conditions, controlled conditions, are going to be implemented in the code. It is going to be a little bit different from the theory, but the main concepts are going to be the same. So let's see how it is going to be. Let's get back to the coding part. We don't need this logging message now. I'm going to write down our requirements first. We need a distance tolerance and we need angle tolerance. Let's set it 0.3 and angle to be 0.3 as well, giving random values. As from the theory part, we understand that we need an angle error, that is from our robot, and the goal pose. So we are going to say goal theta minus pose dot theta. That is going to give the angle from our robot current orientation to the goal orientation, because if we don't drive the robot, angle is not computed. The next part is to drive the robot, and for the driving part we know that we have this linear velocity to drive the robot in linear x, that is what we require, and as well as driving it in an angular motion. These are the two things that we would be needing. Coming to the point that conditions are going to be applied. If angle error, which is robot angle to the goal, is subtracted and we get an error, it is greater than an angular tolerance, then you are going to send this linear velocity, meaning that whenever the angle error is greater than angle tolerance, meaning we have not reached the required part, you are going to be driving the robot with certain velocity, with angular velocity. Once that is done, then you are going to make the robot move for the distance, and for the distance as well we are going to say if the distance to goal is greater than the distance tolerance, meaning that we have reached the goal or not. So distance tolerance is checked, and if the distance to goal is greater than the tolerance, we are going to make the robot drive. With the help of this command, we are going to say this is fixed velocity that you are going to be utilizing to drive towards the goal. And once we have this condition false as well, we are going to say that quit the code, Before leaving the code, it would be a good practice to utilize the logger function, and here you say that goal reached. And that's it. This is our go to goal. We need some improvements. There are some logical errors. Let's run the code and see the output. Here on our terminal, let's first perform call and build, bring in the turtlesim. If I bring the node and I bring it to 991.7, let's send it. It has changed the angle and now it is moving towards the goal. I don't think so it's exactly 9 by 9, but let me print out the data. And yes, you can see the robot has started to collide with the wall. The problem would be it has not taken the accurate turns. That's why it is not reaching the goal. That's a big problem. If I stop that and ask the robot to reach 1 and this time I am going to ROS2 topic echo the state of the turtle. It is going to tell me that theta is this and the robot is not taking any action. Let me stop this node and call the service to reset the robot and again echo the pose. This time I am going to give this angle and let's see what happens. So you can see it is now increasing again and again, although I am giving a different value 1.57. So this code has some problem with it. That's the difference between theory and practice. We have to fix the values first. The first thing that would be an appropriate change is going to be removing this velocity, as we are going to directly supply the value of angle error. The robot rotates, the angle reduces, and so the velocity should also reduce. And also same with the distance to goal. We are directly going to supply those values of error. Let's now run the simulation. Here you can see that our turtle is here. Let's run the same node, but we need to perform call and build first. And now our robot has started to just shoot into the upper boundary. So there is still some error, and the error can be related to the angle. The first thought that I have, because the error changes when we have rotated to a certain value, it changes to a negative value. For example, if I run the simulation and I also open a terminal, I have to stop the node and I drive the robot. ROS2 run ROS2 run turtlesim turtle tell. Now if I rotate the robot, you can see the theta is increasing, and after a certain value this theta has turned to negative. When it goes to anti-clockwise rotation at a certain angle, after that it turns to negative and then reduces to 0, this theta value. One another mistake can be your own programming mistake, and that is very obvious here, because you can see in angle error the robot is not rotating in a proper direction. So angle error is causing some problem, although the logic is all fine. So you can see that I am not using the angle to goal, which is a mistake, and I have to subtract the robot pose from angle to goal, and then the robot can actually make the move towards the goal. And I have to send the linear velocity to be 0, and this has to be float. So I think the code is all ready. Now let's perform call and build and give goal to be 1 and 1.7. Now let's run it. Now robot has rotated and it is now going to start moving towards the goal. We can increase the refresh rate so it can move fastly, or we can also add some proportional constants to our motion. It has reached goal read, it has now stopped. What I'm going to do is to add a proportional controller, which is from control systems, and that is mainly known to be KP. So I'm going to say KP value is 1.2. It's a constant that you fine tune according to your application. I can multiply that proportional constant directly to the velocities, and we can take a look into the behavior of a robot. Mostly proportional constant is part of PID control, that P as is proportional controller, and it is multiplied by the error. It should not be multiplied directly to the distance to the goal, which is directly sent to the velocity, but it should be multiplied with an error. But as this simulation is really basic, so I am going to utilize the freehand that it is providing. Let's make it move towards 9 in x, 8 in y, and 1.7. Now the response is going to be quite faster. You can see it is quite faster, and it is applying the brakes more because of the proportional constant and as we have supplied the distance to goal. If I supply distance to goal to be a linear velocity of 0.6 until the goal has been reached, that can also work. This time it is just going to move slowly according to the value, that is 0.6, and kp is also a constant, so it is now going to move slowly towards the goal, and there is no feedback for the error. So I think the previous one is fine. As the goal reaches, it slows down. As the goal is far away, it gets way faster. And as it is a simulation, we can directly give a higher value and play with it as well. Let's see the final response for robot. Oh, you can see in simulation you can do such kind of things. In real time you cannot do that. It overshoots a little bit and then came back. So this is it for the first lecture about mathematics in robotics. I hope you have extracted the information that I wanted to deliver about small physics formulas to be extracted and utilized into our programming practices, and mathematics, multiplication and subtraction to be utilized for smoothing for our robot's motion. Keep in mind that whenever it comes to velocities, it starts from gravity, Newton laws, and then velocities and acceleration. This is the hierarchy, and whenever this happens, you have to understand the implementation requires timestamps, positions, and derivative and integrals. We have not discussed those in detail here, but these are very important key aspects whenever we deal with the motion of any body in 2D space or 3D space. Currently our level is easier because we are dealing with mobile robots on the ground. I hope in the next upcoming lectures we'll understand more critical things and put kinematics into test as well on real robot.